Assalamu alaikum students, I'm your course instructor Muhammad Kashif and the course name is Design and Analysis of Algorithm. In previous lecture we have covered different topics related to the graph theory, and we discussed what is the definition of graph and what type of graph we can use to implement our real life problems. And we have seen that we have connected graph, we have directed graph, we have undirected graph, and we have a type of graph that is a complete graph, and we have seen an example of all these type of graphs. And we have covered a type of graph that is called bipartite graph. In that particular graph, our vertices or nodes can be represented in a partition, and pair of vertices exist on a path. And we have seen a lot of examples related to the trees which can be implemented by using graph theory. And we discussed about how we can implement our problems that are related to the tree and graph used to implement our problems that can be divided into multiple sections or into multiple modules. And we analyze how we can make multiple childs or multiple sub-modules of a single node or a single parent, because when we solve our problem in a tree, or you can say we have binary trees in which each level a parent node has two children. But what if we have multiple children on a specific node? Then we have to do some more algorithms, or some more, we need to explore further more complex, or the methods that can help us to build or to create multiple nodes on a single parent node. So graph is the solution of all these type of problems, and we discussed how we can solve transportation problems by using graph theory, how we can implement the traveling salesman problems by using graph theory, and we can find the shortest distance path by using the graph theory. So all these application areas can be implemented or can be solved by graph theory. In today's lecture we are going to cover the adjacency list or adjacency matrix, how we can represent the number of nodes in the form of adjacency list, because we have seen that a lot of nodes or multiple nodes are connected with a single node. Then obviously there should be a mechanism, there should be a representation of all these connected nodes, and obviously we want to store all these nodes in a data structure or in the form of structure. So we are going to represent our data in the form where we can say that the nodes are connected with each other, and according to the situation, according to the connection, we are going to build the adjacency list, or we will build adjacency matrix. Then we will discuss about the dense matrix or the sparse matrix, and we create a difference between these two types of matrices. So in today's lecture we are going to discuss these agenda items, and you will learn how we can represent the data while we are using graph theory, and we can represent our data elements or data values into a matrix or into in the form of array. Now let's discuss about representing graphs in the form of adjacency lists. So in adjacency list, each vertex u belongs to the V contains an adjacency list of the set of vertices V such that there exists an edge. Obviously we already discussed in previous lecture that when the nodes are connected with each other, so there must be exist an edge, there must be existing a link between two nodes. So without an edge or without a link, we cannot say, or we cannot make communication between two communicating devices, between two nodes, or whatever you have in a medium. So as you can see here, we have multiple nodes A, B, D, E and C. All these nodes are connected with each other, right? So when I want to communicate from A to B, obviously I have an edge, I have a link between A and B, and I can move from A to B. So when I will I will communicate from A to B, obviously I need to represent my flow of data, how I can move from one place to another place. So as you can see on a slide, I can move from A to B. So I placed an arrow sign from A to B because obviously it's an undirected graph because I do not have any direction. But when I represent this graph in adjacency list, then I have to show the movement or the direction where I am actually moving. So here I am moving from A to B, so I just place an arrow sign from A to B because I am representing my data movement from point A to point B. And obviously as a graph, you can see on the left we have a graph, and in this particular example I can move from B to D and B to A to D. So if I need to represent this graph in the form of adjacency list, so first of all I need to identify how many nodes are connected with a single node. So A has two adjacent node, and if I am on a B node, then I can see that I have two adjacent nodes, that is A and D. And if I am on a D point, I can see I have four adjacent nodes, that is A, B, E and C. That means I can move from D to anywhere, right? But if I want to move and there is a limitation between A, B and D because there is a cyclic path, and I can do a lot of things in a loop where I want to access a data element in a multiple times, right? So if I want to represent these nodes or this graph in the form of adjacency list, so you can see on the right side I have next point, that is a B node, and B is connected with A and D. So I am representing adjacency list of the node B because two nodes are directly connected with B. So obviously I have to mention here the node A, and I place an arrow sign from B to A, and then I place a mark or the arrow sign from A to D because I can move from B to A and then I can move from B to D. So this is the representation of adjacency list that I have mentioned or represent for this graph. And then if I want to move from C to D, then obviously this is the node that could be an input node, and that can transmit or that can send a message to node D. So when I am communicating from C to D, then I need to represent the communication. So the arrow sign represents the communication between C and D, and here I can say that my message is sending from C to D. Now let's talk about the node D, which has four adjacent nodes, and how can I represent? You can see on the right side I can connect all these nodes with D in a way that can represent the communication from D to all the four nodes. So you can see I represent an arrow sign from D to A, then I represent an arrow sign from A to B, and I represent the arrow sign from B to C. Obviously there is no linkage between B and C, but when I need to show the communication or to show the linkages of multiple nodes with a specific node, then I have to represent in this way, right? So I can place an arrow sign from B to C, and obviously I can move to E. So these are the adjacent nodes that I can represent in this way. Now let's see on a last node, that is E, and E has only one adjacent node, that is D. So when I represent this node or the association of this node, I can represent in a way where I can see E is connected with D, and I place an arrow sign from E to D. So this is simply the representation of a graph in the form of adjacency list, where each node is connected with a specific nodes, and the connected nodes are called the adjacent nodes, and adjacent nodes are representing against each node by using an arrow sign, and arrow sign represents the flow of data. And you can place all type of any kind of problem over here in which you are providing data communication, in which you are providing file transfer systems, whatever you can think, you can place over here. Because in computer applications, in computer systems, in IT field, we are just receiving data or we are fetching the data, right? So this graph can be used for your real life problems where you are sending or you are receiving the data. But when you are representing your communication in the form of adjacency list, you can represent this type of adjacency list for your communication between multiple nodes. Now let's discuss another example in which I mark, or you have direction between the nodes, right? In previous example, we do not have any direction, that was undirected graph, but this is a directed graph, because in our previous lecture we have covered multiple types of graphs. So we have undirected graph, and when we have to represent the adjacency list of undirected graph, we can represent in a way. But now we have an example of directed graph, and we can represent the adjacency list of directed graph. So again, in this particular example, we have again edges, but on edges we can see that there are direction available, there are arrow signs available on each node, because we are providing communication, we are sending the data, but we are providing the constraints, we are bounding the devices or the nodes, how they can communicate with each other, what is the source and what could be the destination. So arrow sign represents the destination, and tail represents the source node or source point that can be used to send the data. So if I see on example of graph, I can see the arrow sign pointed that A is sending the data to node B, right? So when I need to show in adjacency list, so I can say there is only one adjacent node available with node A, because arrow sign shows that one node is available with A, or you can say the B is only adjacent node of A. So you can see here I just place only one adjacent node that is associated with A, right? So the arrow sign placed over here, and arrow sign represents the communication from A to B, right? And if we see on a graph, there is no adjacent node available on B, because arrow sign directions are given, and direction show us where we have to move. And obviously B is a node which do not have adjacent node, which B node cannot be used to send or transfer data. B can only receive data, but B cannot be used to send the data. So we are not going to make an adjacent node of B. So there is no adjacent node available on a B node. So obviously we couldn't make or place the adjacent node in adjacency list. Now let's talk about the node D, and you can see D has two direction. D can send the data to node A, and D can also send the data to node B. So there are two arrow signs that are available from node D, and if you see on a adjacency list, on the right side we have node D, and there are two adjacent nodes A and B, and I place here in a way that represents the communication between, or the among D, A and B. Now let's talk about the node C, which has only one adjacent node, because only one arrow sign represents the communication from C to D. So we can place these nodes like this, because C node sending the data to node D, right? So there is only one adjacent node. Now if we move on a next node that is available in a graph, and E node can send data to the node D, so we can place in adjacency list to show the communication or to show the linkage between E and D. So E can send the data to node D. So this is how we can represent the data in the form of adjacency list. Either we have a directed graph or we have a undirected. Let's see another example of if we look into this example. We have another example where we have a graph, and this is undirected graph, and if we want to represent this graph in adjacency list, so we can do that, because we have multiple nodes over here, and A can be communicated with B and D, so I placed in adjacency list, and B can be communicated with A and D, so I placed both the adjacent nodes on the right side. And if if we want to represent the adjacent node of D, so obviously D can be communicated with 4 adjacent nodes that are A, B, E and C, and all these nodes are available in adjacency list. You can see that. And if we want to write the adjacent node of E, so there are 3 nodes available that are directly connected with node E, so we can represent, and obviously I mentioned here how we can represent their communication. And now let's move on a F node. So there is only one node available that is adjacent to F, so that is only E, so I represent here. And if I talk about the node G has direct link with E, so I placed the communication of both the nodes over here. So this was another example that we have seen in which, or you can say that we can represent any type of graph in the form of adjacency list. Now let's talk about the adjacency matrix, right? So in matrix you can see that we have rows and columns, and we can represent our data values in the form of matrices, because our problem in real life, because obviously we have already studied data structures, and in data structures we have 2D arrays, we have 3D arrays, because lots of problems can be implemented in 2D arrays or in 3D arrays. So we can represent our data in the form of matrices. So in matrices we have rows and columns, and there is a rule that we have to follow, that we have to use to implement our problem in the form of matrix when we are represent graph in the form of matrices. So there are 2 conditions that we are going to represent the adjacency, but on the basis of adjacency we can place those adjacent node in a matrix. So first of all, we need to place all the nodes in the form of row and in the form of column. So as you can see on a slide, we have A, B, C, D, E nodes that can be placed in a way. On a left we have column and we have rows. So we represent, or we mentioned all the nodes here in a row form or in a column form. So if I or J belongs to edge, that means if any node, if 2 nodes have an edge, that means 2 nodes are communicating with each other. So we just need to place a 1 binary bit against each communication. For example, if I can see that A can be communicate with node B, then I need to show the communication on a particular row and column. And as you can see, A can be directly communicate with node B. So when I represent my data values in the form of column and in the form of rows, then on a respective row and column I have to mention a binary bit 1, right? That binary bit 1, or the number 1 shows that A and B are directly communicating with each other, right? So as you can see, if A is communicating with node B, then I only place 1 on a respective row and column where I can see the communication between A and B. And now if I am on a node A, then I can see A is also communicating with D. So A can also send the message to D, because B and D both are the adjacent node of A. So on respective row and column, I just need to place 1 against B and D. As you can see, if because I am talking about the first row and the first column, and you can see on a B point I place 1, and I placed 1 over here, because these 1 represents that D and B can communicate with A. Now let's talk about my next node, and next node is B, and B is also communicating with A and D. So I just need to place 1 against the column A and column D. So as you can see, I placed 1 over here, and I placed 1 against the column D, right? So now let's talk about the next node that I placed in matrix, that is C. So if I look on a graph, C has only 1 adjacent node, and that is D. So when I place when I need to place 1 on a respective column, then I have to check the adjacent node, and that is D. And as you can see that I just place 1 over here on a respective row and column. And obviously we have node D, and D has 4 adjacent nodes, A, B, C and E. And when I place these adjacent nodes into the matrix, then you can see that on each respective row and column I place 1 on all the locations where A, B, C or E are available, right? So now let's discuss about the last node, and we have node E, and E has only 1 adjacent node, that is D. So if you move on a matrix, you can see that I placed 1 over here where D is available, right? So if we need to trace, or if we need to analyze this matrix, you can see that we have zeros available on a diagonal, right? So it's a symmetric, right? We have a symmetric available over here. We can see that when we are representing our graph in the form of matrix, there must be symmetric available, and symmetry says that we will got zeros on diagonal positions, right? So this is the condition, because we have undirected graph, and we have got this type of matrix, right, where we have all the zeros on diagonal positions. Now let's discuss about all these iterations. I already have show you all the iterations, and on our first iteration we have 1, and if we move on a node B, we have adjacency nodes A and D. If we move on node D, we have 4 adjacent nodes, and if we can see the symmetric of this problem, we have zeros on the position of diagonal. Right now let's discuss about the directed graph. If we have direction available in the graph, how we can represent the graph in the form of matrix. So the same procedure, same method we will adopt. We just need to place 1 against each connected node, and otherwise we will place zeros. So as you can see, we have direction available from A to B, so we can say that the A can send the message to the node B. So direction says only A can send the data to B, right? So if we want to place these nodes into the matrix, you can see that only 1 place against node B here, and all the places are, or all the locations are mentioned as 0, right? And if we move on to the next node, that is B, you can see that we cannot move from B to any node, right? Because B can only receive the data, B cannot send the data. So if you look on to the matrix, there is no location, or you can say we do not have any 1 on any location, right? So all the zeros are placed here. And if we move to the next node, that is C, so in a graph we can move from C to D. So direction is available, and direction says that C can send the data to the node D. And if we place this communication on matrix, so it shows that we placed 1 over here against D, and rest of the positions are zeros, right? And if we move on to the next node, that is D, so D can only send the data to node A, and D can send the data to node B. So in a matrix we have 1 against 2 columns, and that are A and B, or rest of the positions are zeros. And if we talk about node E, the E can only send the signal to D, or you can say that E can only send the data to node D, and we have 1 in a matrix against column D, right? So in this particular example, you can see that we have again got a symmetry. And symmetry, what type of symmetry? We have zeros on all diagonal positions, right? So this is the representation of graph in the form of matrix. Now let's discuss about the difference between adjacency list and adjacency matrix. An adjacency list is basically a collection of unordered lists used to represent a finite graph. Each describes the set of neighbors of a vertex in the graph. And obviously we have already discussed, and I show you examples in which we represent all the adjacent nodes and all the the connected nodes that are communicate with a specific node. So in adjacency list we represent all the adjacent nodes that can transmit the signal, that can send or receive the files or data. In adjacency matrix, this is again the same thing, or in adjacency matrix it's a square matrix and used to represent a finite graph. It is again used to represent our finite graph, because we have values that can be calculated, that can be stored, or that can be fetched in any time, right? The elements of the matrix indicate whether pairs of vertices are adjacent or not in the graph. So this is the difference between adjacency matrix and adjacency list, because in adjacency matrix we have to show or we can see the pair of vertices are communicating with each other. So if the graph is undirected, the adjacency matrix is symmetric. So this is the difference between adjacency list and adjacency matrix. Now let's discuss about the weighted graph, because we have a type of graph in which we studied, or we have analyzed that if I want to move from one location to another location, there must be a cost. We have multiple costs available in our computer systems, because if I want to send the data from CPU to the cache, that would have a different cost, and if I want to send the data from CPU to RAM, that would cost different, right? That would be a different cost. So obviously there are different weights available on each node when nodes are communicating with each other. So we have an example of weighted graph where all the nodes are communicating with each other, and all these nodes have edges, and each edge we have mentioned a cost over here. So as you can see, we have cost of 8 between A and B. If I want to send the data from A to B, we have a cost of 8, and if I want to send the data from A to D, we have a cost 3. You can map this problem to in your real life problems where you are traveling through Uber or Careem, or if you are using Google Map and Uber Careem are working, they are calculating their fares, they are calculating the distance by using this type of graph, where if you want to move from one, if you choose a path where has a shortest distance, then definitely you have a different cost. And if you choose a long route, then definitely you will be charged high prices, right? How they calculated, how they find or calculate your fare, they just compare and they just calculate the amount that we are associated, that we are placed on each edge, and edge basically connecting the nodes, right? And we have multiple roads, we have lot of tracks or paths that we can use to travel from one place to another place. Like if you are using GT road to travel from Lahore to Islamabad, that there will be a different path, and obviously you will be charged differently. And if you use motorway to travel from Lahore to Islamabad, then definitely the distance or the fare or the cost would be different. So these are basically weight that are associated on each path or each edge that connects multiple nodes, that connects multiple roads. Similarly, if we are using computer systems and web applications or social sites, what we are doing, we are obviously doing fetching data, we are storing our data. Let's see, if we are using Facebook, if we are using Instagram, we consistently sending data, we are consistently receiving data. And what companies do, companies are placing their data centers in a specific territory, in a specific region where they think traffic is increasing day by day. So we have data centers available in India where we are getting the data, we are actually storing the data, because what is the purpose behind to place the data centers or warehouses in India? Because it covers all the Asian regions where users are accessing the data, where user are places the data, because it gives you the fastest communication. And if we are accessing the servers that are available in America or in Netherlands or Switzerland, then we have to pay more cost, right? So there would be a little bit delay in fetching the data, or there would be a little bit delay in storing the data. So this is the reason why we are assigning the weights on each edge, because these weights can be used to calculate the cost or calculate the paths that we are using to access a particular node or a particular device. So if we want to represent the adjacency list of a weighted graph, we can say that A has two adjacent nodes, B and D. So on a B node we have weight 8, so we placed 8 against B, and we placed weight 3 against node D. And we can obviously represent this problem in the form of matrix, and you can see that I just place the cost against each communicating nodes, and because I want to communicate from A to B, and I place 8 over here against the column B, and I am paying the cost of 3 to communicate from A to D. So you can see in a matrix I placed 3 over here. So this is how we can represent our data in the form of adjacency list or in the form of matrices, right? And rest of the positions are zeros, and you can see that we have zeros on diagonal positions. So same conditions that we are going to use when we are representing weighted graph in the form of matrices or the adjacency list. So here we have the condition, we use weight, rather we use a constant value that was 1, and in previous examples we have used 1, but here we are going to use only weight against each communicating node, and rest of the nodes are zeros. Now let's discuss about the sparse matrix and dense matrix. Sparse matrix is a matrix in which most of the elements are zeros, right? and in diagonal we got the values. We can have values on diagonals, right? But by contrast, if most of the elements are non-zero, then the matrix is considered dense, right? So as the name suggests you the meaning, dense means a filled matrix, right? And a sparse matrix is a matrix in which most of the elements are zero, right? That means this is the example of a sparse matrix where we have a lot of zeros available in our positions or in our locations, right? But if I want to represent the matrix of a dense matrix, then there must be you know, the values that are non-zeros. We have lots of most of the elements are non-zero. So this is the only difference between sparse matrix and dense matrix. These are representations of data, representations of graph that we can use to show the working, show the communication between multiple nodes. So the key points are we have covered multiple topics, like we have seen adjacency list, in which we are going to represent our data in the form of a list where we have connected nodes, and we have to show the working of our graph where we are sending the data, what type of nodes are getting the data and what nodes are sending your data. So adjacency list representation, the flow of data, how we can send, how we can receive our data values. And obviously we can use adjacency list for the undirected or directed graph, where we have directions and where we are bound our systems, or we are going to bound our nodes, which nodes are sending the data. So there should be a source node and there should be a receiving node who receiving the data, and we can show these working in the form of adjacency list. And obviously we have covered adjacency matrix, in which we represent our data in form of 2D arrays and 3D arrays, because in data structures we are implementing our problem in 2D and 3D arrays, so we can represent our data in the form of matrix. But when we represent our data in the form of matrix, we have to place the binary bit 1 against each communicating node, right? So on our respective row and column, we just place 1 and the rest of the positions would be 0. This was the adjacency matrix. And obviously we can use this method to represent the directed graph or to undirected graph. And we have sparse matrix and we have dense matrix. In sparse matrix we have a lot of values that are zeros, but in dense matrix we have non-zeros values are lesser than the sparse matrix. So this is all about today's lecture. If you have any question, you can ask to me. Thank you so much.